Hello and thank you for your interest in today's presentation. Today marks the beginning of a series of webinars focused on underground excavation rock stability assessment using Universal Discontinuity Index. In this first lecture, we will introduce the theoretical framework and rationale behind the Universal Discontinuity Index. This novel system represents the first purely quantitative approach to characterizing discontinuous rock masses. It is grounded in the principles of fracture mechanics and damage theory, offering a comprehensive method for assessing rock stability. My name is Amin Hekmatnejad, and I'm a professor in the Department of Mining Engineering at Catholic University of Chile. Additionally, I'm an associate researcher at the Center of Mathematical Modeling of the University of Chile, where I collaborate with mathematicians and scientists on research toward digital mining. I began my academic career in mining engineering, where I obtained both my bachelor's and master's degrees, specializing in mining exploration. I later earned my PhD from the University of Chile, focusing on geostatistical modeling of discrete fracture networks for geomechanical applications in heterogeneous fracture media. Before my academic tenure, I gained valuable industry experience in the petroleum sector, working in geology and geomechanics departments. This role deepened my understanding of the advanced technology and methodologies employed in the oil industry and broadened my skill set in rock mechanics. My multidisciplinary training and experiences have led me to develop integrated approach to solve complex problems in the modern era of rock mechanics. My research interest includes the rock physics, hybrid probabilistic process-based fracture network modeling, computational geomechanics and high computational efficiency, geostatistics, and statistical learning approaches for decision-making in mining application. I divided this lecture into three main parts. First, we will start with a short introduction to the impact of discontinuities on rock behavior. We will explore how fractures, or equivalently discontinuities, influence the rock behavior under load at both the micro and macro scales. Next, we will explore the foundation principle of damage mechanics, which is integral to the Universal Discontinuity Index. I will introduce some new concepts and definitions that are critical for solving complex issues in applied rock mechanics, especially in mining. Building upon our understanding from the first two parts, in the final part of this lecture, we will discuss the formulation of the UD system. We will examine the rationale behind the selection of each variable within the index and discuss their significance. It is well known that the primary factor contributing to the anisotropic, non-elastic, and discontinuous behavior of rock masses is the system of fractures or discontinuities within the rock material. Furthermore, the engineering properties of rock mass are significantly influenced by its system of discontinuities rather than by strength of intact rock itself, both at micro scale and macro scale. This slide revisits the PhD thesis of Amin Hekmatnejad, 2013, which conducted by my underground student in 2019. Here I present a segment of the results. The objective is to demonstrate how microcracks and minerals heterogeneity affect rock behavior at laboratory scale. Here, the analog image displays results from an experimental Brazilian test which recorded a tensile strength of 6.15 megapascal. Additionally, the trajectory of the fractures as well as subsequent rupture paths based on three scenarios, the scenarios A, B, C, are superimposed onto a specimen image. The trajectory, the white trajectory related to the experiment A, the yellow trajectory is related to experiment B, and the blue trajectory is related to experiment C. As you can see, three experiments were designed from left to right, experiment A, B, and C. In the A, homogenization techniques were applied to capture the rock mass strain subjected to the Brazilian test. And you can see the result is 16.7 megapascal, which is quite far from the reality of the experimental test. In the experiment B, or the second experiment, image processing techniques were used to capture the heterogeneity of the rock material, here the minerals, and incorporate it into numerical modeling, which improved the numerical results compared to the laboratory observation. As you can see, here the results is 13.6 megapascal, which is closer to the experimental results. However, it's far from the reality. In the third experiment, based on thin section and microscopic analysis, the stochastic parameters of the system of microfractures were introduced into numerical modeling. The results are quite close to those observed in the laboratory. As you can see, the obtained results based on the numerical modeling here, incorporating both mineral heterogeneity and microcracks into numerical modeling, is 6.96 megapascal, which is quite close to the experimental results of the 6.15 megapascal. As illustrated, enhancing the characterization of rock substantially increased the correlation between the numerical models and the laboratory experiment outcomes. We saw incorporation the mineral heterogeneity reduce the error, and incorporation both microcracks and mineral heterogeneity give us a quite better results. And as you can see, the most notable improvement is achieved when microcracks in the experiment C are integrated into the model, highlighting the critical influence of discontinuity system on the actual behavior of rock material. Moving forward, let's explore how fracture system influence the perturbation of induced stress, which in turn affects the depth and shape of induced damage zone around a tunnel. This discussion is informed by research of Ley et al., which examines the impact of natural discontinuities on the stress and damage induced around a tunnel. This series of experiments, here 9 experiments, illustrate a consistent setup. A circular tunnel with a diameter of 4 meters within a study area of 40 by 40 meters, all subjected to the same stress field with principal stress components of 8 megapascal vertically and 16 megapascal horizontally. The variable across these 9 experiments is the fracture system parameters, particularly the size of the fracture, which is controlled by factor A, which belongs to the power distribution. The higher value of the A means the smaller size of the fractures, and the smaller value of A means larger fracture length. Additionally, the parameters P21, the average length of the fracture per unit area of the rock mass, measure the intensity of fracturing. Higher P21, as you can see, denotes a more fractured rock masses. These factors, 21 and the size, are crucial as we examine the interaction between the fracture system and the damage zone surrounding the tunnel. The experiments demonstrate that for a constant value of P21, for example, in this series of the experiment, an increase in A tends to confine the stress field closer to tunnel. As you can see, the increasing the A means the limitation on confining the induced stress close to the perimeter of tunnel. Align with the principle of continuum mechanics and resulting the behavior more akin to the continuous medium. By reducing the size of the fracture, the communication and interaction between the fracture decreased and the behavior of the media is closer to the continuum media. However, here, higher P20 values, as you can see vertically, for a higher value of P21, leads to the stress field extend farther from the tunnel, up to 10 times the tunnel diameter. As you can see, increasing for a constant value of the A, for example, for larger length of the fracture, by increasing the P21, the induced damage zone goes far from the tunnel perimeter. We now shift our focus to how these conditions affect the nucleation of new fracture or damage zone due to the change the surrounding discontinuity network. Here, in this figure, the red circle shows the nucleation of a new fracture around the tunnel, results of tunneling. Observation indicates that the geometry and occurrence of new fracture vary significantly based on parameters of the discontinuity system. As you can see, by changing the variable A and P21, the nucleation, the number of the induced new fractures, and the geometry, which we represent with the ellipse, is changing. And in scenarios with longer fractures, for constant value of A equal to 1.5, and for example P21 equal to 3, the induced damage zone is more severe, both the number of the new nucleated fractures and also the extension. And this is very important to consider. In this slide, we introduce the continuous damage model. Referring to this picture, SD denotes the damage area of a specimen. In our model, we consider only fracture as forms of damage, as you can see here, characterized by having two dimensions significantly larger than the third. Obviously, in the 3D and in 2D, the one dimension significantly larger than the second dimension. And we exclude any voids. We define two distinct types of stresses. Apparent stress. This is the stress resulting from the load force F applied to the external surface S of the specimen. And effective stress. This is internal stress which exists within the body of the specimen and is calculated by dividing the force F, as you can see here, by the effective load-bearing area, which is defined as the effective section. S bar is equal S, total area of the specimen, or external area of the specimen, minus SD, which SD is damaged surface. Effective stress accurately reflects the stress acting upon the specimen and is always equal to or greater than the apparent stress. Here, according to the principle of equilibrium, this relation, by manipulating this relation, we introduced the damage factor D, which quantifies the extent of the damage. As you can see, here the stress is equal 1 minus d, the damage factor, multiplied by elastic modulus to strain. The damage factor range from 0, the d, range from 0, indicating the intact material with no pre-existing fractures. And it's equal to 1, which represents complete structural failure, where the material is incapable of bearing any further stress. And it is important to highlight that d, the damage factor, is non-linear function influenced by three main variables. First, the discontinuities, including the size, orientation, and the relocation within the material. Second, the stress field, the distribution and the magnitude of stress exerted on the material. And third, fracture toughness, a material property that indicates the material's ability to resist fracturing. Of these three factors, fracture toughness is an intrinsic property of material. In contrast, other two factors, discontinuities and the stress fields, are extrinsic, varying with environmental condition and the nature of the applied load. In this section, we introduce the concept of active and inactive damage as they relate to the material failure. This figure illustrates a scenario where the load direction is perpendicular to fracture plane, as you can see, resulting in maximum effective stress and thus maximum contribution to the specimen degradation. In contrast, in this scenario or in this picture, keeps all parameters the same, except that the fracture planes are now aligned with parallel to the load direction, as you can see. Typically, this would result in the apparent stress aligning with a effective stress, suggesting a damage factor of 0 and implying that the material is undamaged. However, damage does exist. It is merely inactive due to the alignment of discontinuities with a loading direction. These observations, these two extreme examples, lead us to discuss a damage anisotropy. Damage anisotropy describes the variability in how a material degrades or fails depending on the direction of the applied load. This variability is influenced by material's internal structure, such as grain alignment and the orientation of existing cracks, which govern its response to different stress orientation. In this figure, the specimen strength, as you can see, to be lowest under a compressive loading regime when the angle beta between the fracture pole and stress direction reach to a certain threshold beta W. The diagram can be divided, this diagram can be divided in two parts. Firstly, there is a range of angles where the fractures don't affect strength at all, as you can see. And secondly, there is a range where the rock strength varies from its minimum here to the strength of intact rock mass, highlighting that the impact of fracture on anisotropic rock strength varies and depends on their relative orientation with maximum direction of the maximum stress component. In addition to capture damage anisotropy, another critical factor in determining the severity of initial damage is assessing the corresponding state of rock on the stress-strain diagram. The figure here shows that within the fracture system, under a specific field of stress, only subset of fracture contribute to the failure mechanism. These active fractures are highlighted in the red, in the stereo unit also, and are identified according to Coulomb failure criteria. Failure typically initiate from the tips of these specific fractures. The distribution and relative positioning of these fractures, along with rock engineering design, are essential in determining the progressive and non-progressive damage state, which are essential for assessing the likelihood of system failure. In this slide, we explore into the concept of kinematic damage behavior and its essential role in macro-scale application within rock engineering design, with a specific focus on tunneling and slope stability analysis. I'm introducing the extension of this concept into damage characterization for the first time. Kinematic refers to geometrically possible motion of a system or part of a system without regard to the forces involved. This figure demonstrates that the free mass, indicating a block that has separated from the main body, will slip when the ratio of shear stress to normal stress exceeds a critical threshold defined by the friction angle, denoted by mu. However, in practical scenarios, this condition alone doesn't fully determine the failure of rock blocks. In practical cases, the formation of rock block with complex morphology, as you can see in this figure, for example, as illustrated here in the slope scenario, is a critical factor influencing the movement of rock blocks. As you can see, the geometry of the separated rock blocks with respect to the body and the direction of possible failure is very critical to identify the possibility of the failure of the rock block. As you can see in the left hand side in this figure, the separated block is completely stable. However, in the right hand side, based on the geometry of the rock block, this block, the likelihood of the failure of this block is quite high. In the context of the tunneling, as shown here, rock blocks, both of these rock blocks are separate and potentially can fall in the void space of a tunnel. In the left image, as you can see here, displays a completely stable block, while in the right hand side shows an unstable rock blocks. Both depends on the geometry of the rock blocks with respect to the free space, here tunnel, and the body of the rock mass. Notably, contribution to this field include Warburton 1981 with his vector stability analysis of an arbitrary polyhedral rock block with any number of free faces, and Goodman and Shea 1985 with their block theory and its application to rock engineering practice. These examples underscore the kinematic behavior of damage is also a critical factor in assessing the failure potential of rock blocks. Please ensure to retain this section on the damage theory and the various factors that are crucial to the damage factor D. These elements are essential for our understanding and linking the formulation of Universal Discontinuity Index and in analogous factors to this concept. Universal Discontinuity Index represents a novel system for characterizing discontinuous materials. particularly rock. It is important to note that while UD is applicable to any brittle material with pre-existing defects such as cracks or fractures, our focus here is on rock materials and rock engineering designs. UD is a measure of a severity of initial damage for a specific rock engineering design. As this equation shows, UD comprises four main factors. P32 is the total volumetric fracture intensity. The mean, and its definition is the mean area of fracture per unit volume of rock mass with unit of 1 divided by meter. Circular variance subtotal with respect to the vertical direction is the relative total circular variance that measures the degree of dispersion of the discontinuity orientation from the vertical direction. Circular variance total with respect to the direction of the maximum principal stress is the total circular variance with respect to the direction of a vector forming an angle beta W with the maximum principal stress. N sub AF is the number of active shear fractures according to the Coulomb friction failure criteria. And N sub TF is the total number of fractures within the rock mass. W1, W2, and W3 are weighting factors that depend on rock engineering design. The connection between these factors, along with their analogous in damage theory and failure mechanism, will be discussed in following slides. However, in many cases, the process of failure is not instantaneous. Rather, the evolution of damage occurs at the micro scale. What we observe as a failure is the result of accumulated damage at micro scale. Therefore, failure depends on the degree of initial damage, meaning that rock materials with a higher degree of initial damage are more prone to failure, or equivalently more vulnerable. Understanding the severity of initial damage as an index of vulnerability to failure is crucial. The severity of initial damage involves multiple factors which the Universal Discontinuity Index metric aims to quantify based on a concept of complete system view and deep model integration. The selection of the P32 parameter for a UD system is multifaceted. First, P32 represents the presence of initial damage within rock. It is a non-directional and additive scalar variable. P32 definition encapsulates both the size and number of fractures per unit volume of a rock material. For example, here in this figure, the number of fractures in the rock volume is the same. However, as you can see, only the number of the fractures doesn't reflect the severity of damage. In this case, the P32 is about 0.38, and in this case, the P32 is about 0.01. But the fracture linear intensity or fracture frequency in both figures is equal to 10. These characteristics allows P32 to capture the local distribution of fracturing effectively, which is essential for monitoring the evolution of damage. P32's estimation based on linear mapping is well developed, and it is demonstrated that it is independent of the fracture surface morphology, as you can see here. It serves as a measure of degree of fracturing or the blockiness level of the rock mass, as shown by cases in situ fragmentation and the formation of rock blocks around tunnel or other underground excavation. As you can see here, the increasing of the P32 shows the increasing of blockiness level, and in case of a tunneling, the increase of the P32 increase the likelihood of a formation of a closed rock blocks around a tunnel. Another important aspect of P32 is its alignment with the definition of the fracture energy, defined as energy required to open a unit area of crack surface. P32's additive nature makes it compatible with the concept of multi-failure and the accumulation of damage in seismology, as shown in these pictures. Based on the additivity and non-directionality of the P32, we can track the evolution and accumulation of damage, which is all these together motivate me to consider a P32 as an alternative variable for representing in the Universal Discontinuity Index, which can be helpful to show the severity of an initial damage. Video A and B demonstrate how the direction of the fractures impacts the morphology of rock blocks. As previously highlighted, the orientation of fracture relative to the principal stress components and the morphology of rock blocks are crucial for analyzing rock strength anisotropy and the kinematic feasibility of damage. In these examples, as you can see, the P32 value remains consistent for both sets of the experiment. The P32 is 3. With identical number and area of the fracture, 3 fractures in both cases, and the area of each fracture 3 meters. The key difference lies in the direction of the fractures in each case. In case A, there are 4 rock blocks, each within a volume of 0.25 cubic meters, whereas in the case B, there are 8 blocks, each with a volume of 0.125 cubic meters. So not only the value of the P32 is crucial factor for the formation of the rock blocks, but also their mutual interaction, which is captured or which is influenced by the orientation of the fractures. If the fractures tend to intersect each other, the probability of block forming is higher than in the case where all fractures are parallel. This justifies the introduction of the circular variance parameters, which makes possible to quantify the degree of clustering all fractures belong to the same group are parallel, or the fractures are distributed in all directions. This inclusion enables a more comprehensive characterization of initial damage, taking into account the significant role of fracture orientation. Let's see how. As mentioned, the mutual interaction between the P32 and the circular variance representing the orientation of the fractures is crucial to formation of the closed rock blocks. Fracture orientation can be represented by the direction of the unit vector normal to the fracture plane, similar to how univariate data is characterized by measure of a central tendency and dispersion. Let's assume we have n fractures, each with a corresponding unit vector. The length of the resultant vector from this unit vector is denoted as r here. The circular variance CV is defined as 1 minus r divided by n, where R is the magnitude of the resultant vector, and N is the number of the fracture unit vectors. Notably, the maximum value of R can be N if all vectors are parallel, reflecting identical fracture orientation. In this scenario, the circular variance value is 0. Conversely, here, all the fractures are parallel. Here is the concentration of the fracture poles, which is equivalent to the circular variance value equal to 0. Conversely, if the fracture orientation are uniformly, as you can see here, R will be 0, the sum of the unit vectors, and the corresponding circular variance will be 1, as shown here. According to this equation, circular variance is a non-parametric and a scalar variable which can represent the direction of the fractures. Its value doesn't depend on the number of the fracture sets or the specific distribution of a fracture orientation. Instead, it provides crucial insights into the degree of clustering of fracture orientation. This metric can be estimated both locally and globally as an index of clustering. All these properties of the circular variance with P32 again allows to incorporate the important behavior of the fractures and important factors of the fracture system which are critical for a severity of a initial damage. The computation of a circular variance in relation to the predefined orientation is crucial for assessing the severity of damage. This innovative approach represents the first time the orientation of fractures has been mathematically integrated into the engineering analysis of fracture systems. In this context, multiplying the volume fracture intensity by circular variance relative to the vertical direction, as observed in the roof of a tunnel here, and the subvertical direction toward a void space here of a tunnel, highlights the role of the discontinuities that contribute to the formation of potentially kinematically unstable rock blocks and influence the direction of a motor shear stress. As shown in this picture, it is crucial to accurately assess the direction of a failure along a tunnel walls, where the direction of the block failure on the left wall is toward the right side and the right wall it's vice versa. This assessment is made feasible by calculating the circular variance with respect to these predefined failure directions. It is also worth mentioning that in a separate study which has been submitted to the Journal of Rock Mechanics and Geotechnical Engineering, we introduced an innovation methodology based on the Universal Discontinuity Index for automated full-scale rock block stability at real time. This methodology is validated theoretically and empirically through a comparison with well-established hybrid discrete fracture network Warburton approach. The second factor considers the ratio of fractures that are active for slips along their plane in response to the stress field, compared to the total number of fractures. To classify the active-inactive shear state of fractures, the Coulomb criteria is used. This index is crucial for indicating the evolution of damage in the event of shear failure. For example, if this ratio is 0, it implies that none of the fractures have the potential for shear failure, suggesting that the rock behavior is similar to that of intact rock and likely not yet at the yielding point. At the yielding point, mode 2 or shear failure becomes more probable and the evolution of damage is more dynamic and progressive. To better understand this factor, let's consider dividing the perimeter of a tunnel into several zones: the crown, shoulders, and the wall, as you can see in this figure. Applying this criteria to this section reveals that although there may be many fractures, as you can see, the green dots and the red dots represent all the fractures. You can see here in the 3D more circles, and here the representation of the pole of the fracture in the ester unit. And within the population of all of the fractures, just portion of these fractures are active, depending on the induced stress and relative orientation of the hoop stress and plane of the fractures, which are prone to trigger a slipping of the fractures. Here, as you can see, the ratio between the number of active fractures to number of the total fractures is high, and we can interpret it that we are in such a place in the curve of a stress strain, and it means that the initial state of the damage is more progressive, or we are in the elastoplastic part of the stress-strain curve. However, going to the left top corner or the left shoulder of the tunnel, as you can see, the orientation of the active fractures are changed, and also the number of them, which is as a function of the orientation of the fractures, orientation of the hoop stress, and the value of the hoop stress. And as an interpretation, we can say, okay, in this part of the tunnel, we are, with respect to the crown of the tunnel, we are in a part of the stress-strain curve, which have less progressive initial state of a damage. And for example, in the left wall of the tunnel, as you can see, the number of the active fracture is quite low, and we can interpret that we are in the part of the elastic or more elastic part of the stress-strain curve, and the state of damage is not progressive. Also, interestingly, we can see the role of a shear failure at the wall is less significant than the other two zones of the tunnel, providing insight also about the potential of the other failure mechanism, like a block failure instead of a shear failure. Based on what I presented, we can conclude that a UD is a robust measure of severity of damage, initial damage, based on deterministic and probabilistic damage theory. UD consider 5 factors among six factors that are influencing the severity of damage, including the factors of stress, the magnitude of the stress and its distribution, and the factors related to the discontinuity population, including size, orientation, and location. Also, UD has a unit of a measurement, divided by meter. UD is based on the complete system view and model integration. Universal Discontinuity Index, based on its formulation, is an objective system for characterizing rock mass. And also, UDI can be applied from lab scale to real scale practices. Here are the list of upcoming lecture series topic related to the UD and its application. Assessment of the severity and shape of the rock failure along a tunnel at El Teniente mine, Chile. enhancing semantic models in digital twin representation of rock mass using Universal Discontinuity Index, real-time full-scale UDI-based method for automated tunnel rock block failure risk assessment based on the borehole data, theoretical and empirical validation against the hybrid DFN Warburton approach, and lab scale and numerical modeling approach validation of the UDI as a measure of the initial damage severity. Thank you again for your interest in this presentation, and hope see you for next topics of this presentation.